Hello and welcome back to Innovation Insights. Today we are joined by Dr. Jeremy Knopp, Chief Technology Officer at Armatus, a dual-use technology startup operating in Japan, the US, and Australia. Hi, Jeremy. Thank you for being here.
Hi, Victor. It's a pleasure to be here. Thank you for inviting me.
Oh, my pleasure. So I want to start by a little bit introducing yourself. And can you tell us a little bit your story, your path into getting here and sitting here with us in this podcast? How did it go from you starting your career, your professional career in research, and getting into being the Chief Technology Officer here at Armatus?
Well, it's been a long journey, and I think I'm going to start with one summer in 1996. I was in Ohio working at a factory that manufactured shampoo and conditioner. And it was a very hot day. It was about 40 C, and I was moving drums of shampoo and conditioner that were quite heavy. And as you can see, I'm a small person. And I thought to myself, I can't really continue doing this work much longer. I was only 18 years old. And I come from Ohio. It's a manufacturing state. And there was really no expectation on me to even attend university. But I was always good in math, and I had a desire to do something with my life. So I enrolled in a community college. It's called Sinclair Community College in Dayton, Ohio. And I have a very high opinion of community colleges. I think they do a lot of good across the United States. Here in Japan, the equivalent would probably be something like Kosen, which is a technical school for kids aged 16 to 20. I guess my experience was similar to something like that. But that was my start. And I'm really thankful for that opportunity. And I'm thankful for the people that, created those opportunities for people that, might not have a chance to go to the university right out of high school. So that's where everything started for me. And I had a personal interest in physics. And there was a modern physics course that was offered at Sinclair one summer. It wasn't a requirement, but I decided it was interesting enough I wanted to take it. The adjunct instructor, his name is Sean Kirkpatrick, and some people listening to this may know that name. He ultimately created the AARO office at the Pentagon in the US, which stands for Air Anomaly Resolution Office. And it's also known as the UFO office.
There you go. Thank you for that.
And so, he's been on television recently. And I actually took a class from him when he was a fresh PhD graduate. And that was definitely a turning point for me to actually be interacting with a brilliant man like him. And I found out about internships at AFRL, which is the headquarters is at Wright-Patterson Air Force Base in Ohio. And I worked with him to actually become a student researcher there in AFRL.
Yeah. So the UFO stories inspire you into going into research with the Air Force.
Yes. And at the time, I think he didn't even know he was going to be standing up such an office. He had a very long career, started with basic research, and then he ended up doing a lot of things in the United States government.
Right. But you ended up from that beginning in entering the Air Force Research Laboratory. You ended up leading this huge research program here in Asia and overseeing multiple researchers. And that gave you an overview of a lot of different technologies. Can you talk a little bit more about what is that like? How do you oversee such a program? How do you start thinking what is more interesting? How do you choose the things that you want to support more or you advance? And how do you go over that?
Right. So, well, like I said, it's been a long journey. And so once I started working at AFRL, I was exposed to different technical areas, including high temperature ceramics. laser materials, and then I spent a lot of time in a field called non-destructive evaluation. So, for example, the first day on the job, I was testing ceramic fibers for tensile strength. And I was told that these fibers are very hard to purchase. They're only manufactured in Japan. And so please don't make any mistakes because we don't even know if we can purchase these fibers again. And what they were looking at the time was the effect of nano coatings on the strength of the fibers. Ceramics matrix composites are useful for harsh environments. So, for example, the space shuttle used CMCs. Certain types of turbine engines use CMCs. They enable engines to operate at higher temperatures with better thrust and things like that. So from very early on in my career, I knew that there were technological advances that were happening in Japan that were not happening in the US.
Right.
And so that's where I started. And I was basically a bench level researcher, nose to the grindstone for 15 years. I published a lot of papers. I had a chance to do advanced degrees. And at one point, I was working on some problems in non-destructive evaluation, which was my research field. And I noticed a recurring theme where there were engineers sitting on one side of the room and statisticians sitting on the other side, and they didn't seem to like each other very much. And so what I decided to do, and this has been a theme in my career, is to be a bridge between two different communities who really don't speak the same language. And so I actually ended up doing a second master's degree in statistics. And that was my whole goal, was to bridge the engineering community and the statistician community. So I had that experience of trying to see the world from two different points of view. And believe me, statisticians look at the world very differently than engineers.
Yes.
And so then in 2014, I became the assistant chief scientist for the Materials and Manufacturing Directorate. And so for the first time in my career, I actually had to step away from the day-to-day research activities that I was focused on. And this was another turning point for me because my view was widened considerably. Not only was I overseeing all the activities in the Materials and Manufacturing Directorate, which include things ranging from synthetic biology to functional materials to structural materials to advanced manufacturing, but I also joined meetings with the other chief scientists from other directorates throughout AFRL in different geographic locations that would include information technology, for example, or the basic research funding agency, the Air Force Office of Scientific Research, or space vehicles in New Mexico. And so by osmosis, I was learning about all the different R&D activities going on through the entire enterprise. And keep in mind, AFRL has, if you add up all the government and civilians and the contractors, we're talking about 10,000 people with a budget approaching $3 billion a year. So a lot to keep up with.
Right. And then when you come to overseeing the Asia program, right? Yes. And then you have to not only bridge the culture among different disciplines, bridge the culture with different countries and different ways of doing research and looking into that. How do you approach that? How do you approach then the connection of your program with those scientists with different nationalities?
Well, no, it's an excellent question. So in 2016, I was detailed to the Air Force Office of Scientific Research's office here in Tokyo. So there's an office here in Tokyo, and it facilitates basic research collaboration between researchers in the Indo-Pacific region and in the US. And the key word there is basic research. And how would I define that? Basic research basically is openly publishable.
Right.
So all of our activities are in the public domain. And so What was the motivation for that? Why is there an office in Tokyo? And why is there this emphasis on facilitating international collaboration? And it comes down to a very simple truth. The majority of the research and development is being supported outside of the United States Defense Department. That is the reality. Awesome research is going on throughout the entire world. And also we had some programs in place going back a couple of decades. One of my favorites, and one that I ultimately had the opportunity to manage, is the Taiwan Nanoscience Initiative program. And this started out in the year 2000. And what was going on at that time is there was all this enthusiasm about nanotechnology, silicon meets bio, and there were conferences going on. And the leadership, in the United States government at the time was saying, well, why aren't we doing this? Why aren't we? And the reality is if you're spending research dollars on turbine engines, for example, that requires very expensive facilities, expensive people, expensive equipment. You can't just turn a switch on and say, now we're going to get into nanotechnology.
Right.
So what did we do? Well, we looked around the world and we noticed, hey, Taiwan, they're putting $1 billion into nanoscience. And Korea is doing the same thing. And maybe we can leverage their investment and also provide some of our people and our tools and collaborate with them. And so by necessity, for the simple reason that there's limited resources,
right.
There was this need to collaborate internationally. And there's been some analysis done on the output of such international programs. And it turns out, if you look at journal publications that include authors from multiple countries, the impact is actually higher. There's been some analysis on that to show that. So notionally, and I'm not going to say quantitatively, but notionally, qualitatively, there's some goodness in that. Right. And we recognize that. And so when I was in the position at the Tokyo office, I was supporting individual researchers in Singapore, India, Korea, Taiwan, Australia. But I was also facilitating real collaborative, what we call initiative programs, to bring researchers from these countries to collaborate with their US counterparts and facilitate workshops, facilitate joint visits, and encourage the collaboration and publication of results.
No, I love this story because it's also, I think it's very telling when you have this research on very important challenges or frontier challenges. The effort is so huge that it's almost impossible to do it individually. And the example, for instance, is space. How good collaboration has worked into advancing space, right? So you're basically bringing a very similar approach to other challenges like fusion, energy, or others like the nanotechnologies and so on. So it makes a lot of sense, and you can see it directly. So I want to continue this path forward, and you were overseeing and supporting all these individual researchers in this wide area, super interesting fields, very diverse fields, and you have a bird's eye view of all that research in a region which is the top of the world. You look at some science and technology clusters around the world. In Asia, you will pop up like the top 10, 5 are in Asia, and they're here and there, like Singapore, the Koreans, the Japan, and of course China. India is now coming up, and you have that. So from that eyes, from that perspective, wide perspective, what were the technologies or what were the advances that you were most interested about, or that were more breakthrough that you encountered?
Yeah, the ones that excited me the most were ones where maybe I inherited a portfolio and it wasn't my technical area of expertise. Really good example of that is synthetic biology.
Right.
I had no background in biology when I started managing these programs. And to this day, I'm just fascinated by what's going on in synthetic biology. I'll give you two examples. There's a professor at National Taiwan University that's looking at something that he calls cell-free synthetic biology. Give you an example. Silk. The material silk has some amazing properties. The fibers are strong. They have very interesting optical properties, antibacterial properties. And so there was a lot of effort decades ago to see if we could manufacture silk for applications such as composite materials that are strong and durable, and optical fibers and all kinds of things. And it turned out to be a little bit of a disappointment. A lot of time and energy was spent on this, and it didn't really transition. And so I came across this work at National Taiwan University where they were taking a synthetic biology approach. And the idea, and I'm sure I'll be corrected, but notionally what it was is imagine if we could create a fictitious organism that's not necessarily a spider, and that fictitious organism could manufacture, quote unquote, a fiber that's not necessarily from a spider, but from this organism that doesn't even exist. And that's notionally what cell-free synthetic biology is. Right. And so the professor there at NTU has gotten a lot of traction on that, and people who I guess were a little disappointed with the results of the prior investments were overwhelmingly endorsing this path. To give you an example of that, one of the rules that we had is that we had to get external evaluations on any proposals that we would fund. I mean, this is taxpayer-funded grant money, essentially, and there were regulations in place to make sure it was spent wisely. So I needed one external evaluation. So I sent it off to some of my counterparts who work for the U.S. Army Research Laboratory. And next thing I know, I had 7 external reviews where people were actually volunteering their time, to engage in this because they saw the promise. So that's one example with silk fibers where I saw something exciting in synthetic biology. And then another area that was totally different was in this area of gut microbiomes. The biology of the gut bacteria, which sounds gross, but when you really dig into this, so much of your cognitive abilities and your well-being is directly related to the health of your gut. And some of the research we supported there was more looking towards, the cognitive abilities of a pilot. Why are they sleepy? Is there something we can change with probiotics to enhance their awareness and the amount of time that they can fly? But the ramifications of that research, it's already transitioning into areas like personalized medicine because everybody has their unique fingerprint, the microbiome. And so that's an exciting area that I think is going to, encourage significant advances in what you would call med tech, I guess, which is totally separate from what we had in mind. But nevertheless, there's a lot of energy now behind that.
Right. And you were, as you said before, your program was funding this fundamental research, this basic research that then you can translate into different applications. And you see that happening. And I want to go further into this line because when you are doing that and you are such at the beginning of the, let's put it that way, of the ladder of commercialization from the idea of the basic research and understanding how it works scientifically, then you have to go into can we make this happen in a sustainable way or in a way that this is achievable with the resources that we have. And then, of course, if it goes to the market commercial, it can be commercialized and be financially sustainable. But there are sometimes you put the effort, you saw the applications, and it follows its path, and it takes years. Sometimes it goes into the process. Other times you have serendipity and breakthroughs that you don't expect. And do you encounter some of those other paths that happen because of serendipity? And can you give us a good example that you were like saying like that this was totally unexpected, but look at these implications that it had, and it was surprising us, but it's fantastic.
Sure. I mentioned managing the Taiwan Nanoscience Initiative, which incidentally, that's Taiwan's largest international science and technology program. One of my counterparts for that program, his name's M.K. Wu, and he had an amazing career. He's an amazing person. I just met him a month ago, as a matter of fact. He's still actively doing research. He was at the University of Alabama back in the 1980s, and he was working on superconductivity. And superconductivity has been a dream of science fiction authors for a very long time. Progress has been quite slow. But breakthroughs in superconductivity are needed for nuclear fusion and maglev trains, a lot of interesting applications for high temperature superconductivity. One of his students, I hope I remember the name right, Jim Ashburn, I believe is his name, was a graduate student, nose to the grindstone, doing research, and he kind of went off course a little bit, didn't follow the instructions exactly as he was supposed to. The main point here is the more students we have in the lab turning knobs, engaging in the research, the better off we're all going to be. Well, it turns out he didn't follow the script from the professor. He used the wrong oven. It went to a higher temperature than they intended. He actually did a few more experiments than were originally planned. And there were a couple other, I guess you could call them, quote unquote, mistakes along the way. But by golly, one of the last major advances in high temperature superconductivity came from that graduate student's work at a relatively unknown university. University of Alabama is not known for superconductivity research.
Right.
And the important point there is it really doesn't matter what school you're in. It doesn't matter your position. This was a graduate student in a normal university,
right,
who made just an incredible breakthrough in high temperature superconductivity. And it was a serendipity kind of thing. This was not pre-planned. And that went on to inspire other scientists and engineers to work on different high temperature superconducting materials, which has led us a little bit closer to nuclear fusion. It's led us closer to the maglev trains. And it really did have an impact. So that's one of my favorite stories that I recall that I think is largely forgotten because this did happen a while ago, but I think it's good to resurrect that story.
I really love your story of creative mistakes.
Creative mistakes, that way.
That's right. But that brings the idea of diversity of talent, diversity of perspectives, and even those unconventional ways of approaching things gives you sometimes insights that you would otherwise not look at. So continuing with this path on the commercialization, you are seeing so many examples of how this path goes from the basic research to the application in itself. And I want to ask you, with that perspective, what would be your advice for researchers that have this application and want to tool it into changing the people's life and making them better with their applications because they see a potential use in society that can advance our lives. So what is your perspective now that you've been seeing this during years and seeing the different examples happening? What advice can you provide?
Well, my advice first, I have to just state that this is hard. It's not for the faint-hearted. It's one thing to conduct experiments in the lab, get some results, publish some journal papers. It's quite another thing to transition that into a real world application.
Right.
So there's a huge gulf between the two, and we just have to acknowledge that. And not everything's going to transition into an application. But my advice is to team up with a diverse group of people that have knowledge in different domains, whether that is, with technology accelerators, have to engage with people on the finance side of things, which a lot of technologists aren't comfortable with. They're just like, oh, I didn't study finance. Got to team up with the right people. And it does take a team, right? One of the examples that comes to mind, one of my heroes, I guess you could say, he's a professor at UC Irvine. His name's David Casalius. And what he does is he goes into nature and he finds organisms that exhibit some type of extreme behavior. Maybe it's some type of silkworm that can actually digest rocks, or maybe it's a bacteria that can survive with, very, very low moisture and arid desert conditions. Or maybe it's, one example is a diabolical beetle that you can drive your car over and the beetle doesn't die. Why can they withstand these extreme conditions? And so what he does is he goes into nature, with his, microscopy equipment and tries to understand, what is going on. And I think one of the examples that's been in the news is the mantis shrimp. This mantis shrimp actually packs the most powerful punch found in nature at all, even more powerful than a bullet.
Wow.
But the shrimp continues to thrive even after throwing these punches. Why is that? And so he looked into it, and there's actually a special nanostructured material that prevents damage to the shrimp. And what he's done is he's like, wow, what could I do with that? Well, it turns out a lot. And he has actually, this is a longer story, but there are now helmets and golf clubs that use that same nanostructure for an actual product. So the helmet, and this has direct impact on humans. So now football players can wear a helmet that's much stronger than the conventional helmet and protect themselves from brain injury. And who doesn't want a better golf club, right?
Right.
And so this is an example where he went into the most extreme aspects of nature, understood it, reproduced it with additive manufacturing and different tools that we have now. And now it's in real commercial applications that people are using.
And being able to commercialize, and I'm guessing this is also useful for emergency workers and any other kind of necessity to protect your head, no matter where you are, even climbing activities.
Exactly. Yeah.
So no, it's a fantastic one actually.
Yeah.
And super interesting. We usually end the podcast asking a final question, which is about what kind of breakthrough do you see in technologies that you're more excited about that is going to change our lives in the coming future, nearby coming future? And I want to ask you that because you have a very, very wide perspective of that. And you are now a chief scientist officer. You oversee what is, from fundamental research to breakthrough technologies that can be applied. You're looking now into these applications in a more detailed way. So in the next 5 years, what are you more excited about that you think it could be able to change our lives going forward?
Yeah. So I have to say, I've been focusing on dual use technologies for a while now. And I'm seeing Japan as a country really make a serious investment in space with, for example, their space strategy fund. I mean, this is a kind of a whole of society approach they're taking, where it's led, by the cabinet, but then there's multiple agencies involved. And I just think some amazing things are going to come out of that. I mean, you've already seen a little bit of it with companies like Asher Scale and removing, space debris and things like that. But I think you're going to see advances, for example, in very simple things like cameras. I think you're going to see revolutions in lens designs, for example, with meta optics and meta surfaces and things like that, which are going to impact us, with our iPhone cameras.
Yeah, right.
So that's super exciting. And going back to the original space race, we know that great technologies come out of these challenges with
Right.
space. We're going to be doing things like, growing plants in space.
Right.
And there's going to be advances in electronics. Something that I noticed, I remember the Fukushima disaster, right? And I wasn't here at the time, but I followed the news very closely because I've had some connections with Japan for decades. And I actually have a lot of acquaintances in the nuclear engineering community because I worked in non-destructive evaluation. That's important for the nuclear industry. And one of the challenges was removing or even understanding where the fuel debris was
Right.
in the reactors. And with the high radiation, the electronics just simply weren't survivable. And so that inspired a group of Japanese researchers, I think mainly at Hokkaido University, to take a look at something called diamond semiconductor devices. And diamond semiconductor devices are kind of the perfect power semiconductor that can withstand, harsh radiation environments and things like that. And quite frankly, Japan has great traction on that. They lead and gallium nitride, for example. There's Professor Mori at Osaka University still doing great things there. The best gallium oxide company in the world is right here in Saitama, Japan, with novel crystal technology. And I'm not sure there's another organization anywhere in the world that has made a bet on diamond electronics like Okuma Diamond Semiconductor has. And so they are building a factory right now in Fukushima. That was part of the deal. You had the Fukushima disaster, but there's going to be, incentives to work on these materials that can withstand high radiation environments. But you got to manufacture it in Fukushima. And I think what you're going to find is there's going to be a lot of space applications for these electronic materials because radiation is a huge issue in space. So I think you're going to see developments in optics, electronic materials, biology.
Right.
If we're going to space, you got to understand that. So I'm really excited about what Japan's doing in space. I'm going to be investing more of my time working on different space-related activities. And then I'm excited about a lot of other things too. We touched on synthetic biology. That's going to be a revolution. I think some of the challenges in quantum are going to lead to some, new developments in secure communication, maybe some alternatives to GPS, for example. So yes, there's going to be it's a great time to be in dual-use technologies.
Right, and I love that you brought the Fukushima example with diamond materials because from one extreme environment to the other, and see how a crisis can become an opportunity for innovating and making the best out of it, and develop new applications that can serve us better to humanity. So that was a very, very interesting case of how these crises become an opportunity and innovation can help in that environment.
That's an excellent point because, hey, let's face it, there's a lot of crises right now in our world. And it's hard not to get down about it sometimes. A lot of my colleagues, they'll focus on something going on. But as innovators, we have to lead the way and show how, hey, yes, we don't deny there's a crisis here, whether it be with the environment, but we have no choice but to innovate and be inspired by these crises and do some good.
Exactly, and try to make the best of it to make us sound good and advance as society. Well, thank you so much, Jeremy. It was really a pleasure to have you here.
No, thank you, Victor.
Before we finish this conversation for listeners today, if they want to follow you, if they want to follow your work, what's the best way to connect with you? What's the best way of following what you're doing?
I think LinkedIn is a great tool. I'm very accessible there. I don't post as much as I'd like to. I do post periodically, but I'm always, watching what's going on LinkedIn. And if you send me an invite, Jeremy Knopp, I should come up and happy to connect with you.
Thank you so much, Jeremy. It was a pleasure having you here.
Thank you, Victor.